Good morning, everyone. It's Dan Sandick here from the Institute for Catastrophic Loss Reduction. Thanks for joining us this morning. We've got an excellent webinar lined up for you, and actually several people in the office this morning as well. So today we have Dr. Eric Robinson, who is a senior scientist and manager in AIR's Research and Modeling Department. He's currently responsible for supervising the worldwide development of AIR's extratropical cyclone and severe thunderstorm models. So the presentation today will be about an hour or so, and then we'll have time for questions afterwards. So as in all of our previous webinars, please feel free to post questions throughout the webinar using the question tool, which you should see on the right-hand side of your screen. And there's no need to wait till the end of the webinar to post questions. If you have a question, please post it during the webinar, and then we'll wait till the end to ask questions. I also wanted to let you know about our next webinar. We have our summer break coming up for the next couple of months, and then on September 16th we'll have Francis Weirs in to talk about extreme rainfall and climate change modeling. Francis Weirs is one of the top climate change modelers in Canada and really the world, so it'll be a really good presentation. So check your inboxes over the next few couple of months, and it'll be good to have you there. So with that, I'll pass it over to Dr. Robinson.
All right, thank you very much. So like I said, my name is Eric Robinson. I'm from AIR, and today what I'm going to talk to you about is an application of catastrophe models that maybe is overlooked sometimes, but I think is actually pretty interesting sort of a study on sort of the extreme of the extreme. And so, by their nature, cat models are meant to model catastrophes. But as we all know, there is a wide spectrum of catastrophes. And so what we're going to look at today is the far, far tail of the distribution and discuss a little bit about what that would mean for the Canadian insurance market, some of the feasibilities, and where, at least from my perspective in developing the model, where we really want to spend some time and focus and at least be aware of these possibilities. So we will talk about Canadian mega disasters. There we go. So I want to start off, though, to sort of define, when I say mega disaster, what are we talking about and what types of perils are we interested in? And here's the goal. Here was my goal in putting together the presentation, and is basically to create a plausible yet highly, emphasis on the highly, unlikely scenario that could pose a real shock to the market. So you can imagine the types of losses that the market is capable of absorbing. These are the things that, yeah, maybe it can absorb them, but there's definitely going to be some ripples. And so we want to look at that, look at those values, understand a little bit about whether or not we're prepared for these, what I would view as eventually inevitable events. All right, so what types of events have we seen in the past do I consider to be mega disaster-like? And so we started off by just listing some off the top of my head I could think of across different perils of events that I think at the time that they occurred, they really were a surprise to people as far as not only their amount, but also the fact that we could see something like this. The token example we have here is Hurricane Andrew in 1992. So you can see the loss I have here is about $17 billion, which actually isn't all that extreme in the spectrum of extreme. But at the time, it was really something that was completely and totally unheard of. In fact, I think the number that I found is that in the U.S. alone, we had 7 insurance insolvencies for Hurricane Andrew, and then there was one, I think, international insurer that also went insolvent. That was sort of the birth of catastrophe modeling, of really looking at these extreme events. But it's basically looking at what would be today's Hurricane Andrew, what would be the event that would really shock and awe the market now. Hurricane Katrina is another good example of that in 2005, $61.6 billion. The Tohoku earthquake from 2011, also one of those events that I think really had an impact on the market that nobody was really quite expecting. And then, focusing more on Canada, since the presentation is Canada-centric. One of the great examples is the 1998 North American ice storm. So those of you who live in the Montreal area probably remember how terrible this event was. At the time, it's about $1.5 billion of loss. If you try to do that to today's dollars, that'd probably be about $3 billion. Take into account some of the mitigation measures, maybe bring it back down to $2 billion. But definitely at the time, I don't think anyone saw a month-long power outage in the Montreal area. So that's an event that I think really warrants some discussion. The Fort McMurray fire, which is currently, the total loss amount isn't exactly known yet. I think AIR's estimates were somewhere between $4 to $9 billion, but I don't think anyone really saw that coming, or at least most of us didn't. The Calgary floods as well, 2013, total damage around $5 billion in 2013 from a flooding event. So this is just to give you a sample of the types of events that have these characteristics that we're looking for. So maybe put another way is, what is the next Canadian black swan event? Now, of course, by definition, if we happen to have found a black swan in this presentation, it is no longer a black swan because we've thought of it. But you get the idea, is these large events that nobody really has thought too much about, but really are meteorologically plausible. Okay, so our focus is going to be on the wind perils. That's my expertise, so I'm not going to talk about earthquake. I'm not even going to talk about fires, but I am going to talk about severe thunderstorms, ice storms, hurricanes. That's sort of my wheelhouse, and I think there's a lot of potential just right there. So some pretty extreme events. So tropical cyclone, winter storm, severe thunderstorms. Now I'm going to break this up into 3 sort of steps because I want to show you how do we go about coming up with these events. So you can imagine you could just randomly take a hurricane and put it in the middle of Alberta. That would never happen, right? So we do want an extreme event, but we want something that is still within the realms of possibilities, even if it is sort of pretty far out into the tail. So what I want to show you is sort of the process I go through, the process our company goes through when we try to decide how do we want to create these extreme yet plausible events. Step 2, so step 1 is considering the meteorology. Given the region you're in, what types of perils are you used to seeing? What's possible given the physical nature of that area? Step 2, of course, is consider the exposure. So, a catastrophic event is normally a catastrophe, not necessarily because of the actual event itself, but because of its location. So you can take an EF5 tornado and put it in the middle of a cornfield, and nobody's going to really bat an eye at that. You move that now to Toronto, to Montreal. Now you're talking in terms of catastrophic loss. So we are going to look a little bit at the exposure in Canada and how that affects where these extreme events might occur. And then finally, we want to consider historical experience. So we look at the meteorology, sort of zone in on where we want to focus on. We look at exposure to get a more highly focused area that we want to put the event down in. And then once we kind of create our event, we want to say, okay, how does this look compared to the meteorology and the events that we've seen previously? Is this 100 times more intense than the biggest storm we've ever seen? That might indicate that maybe we've done a little too far with the event. But we still want to feel like it's within the realm of possibilities given what we've seen in the area. So we're going to start with tropical cyclones, which I know is not really the peril that sort of first comes to your mind when you think Canada. But Canada does get tropical cyclones. They average, on average, about 1 landfall every other year, thereabouts. And so we're not talking just hurricanes. These are also sort of the weaker tropical cyclone storms as well. Obviously, given the sort of the nature and the geography of Canada, we're talking basically the maritime provinces here. So I do want to start with, again, step 1, which is consider the meteorology. So in order to create an event that is realistic but still extreme, we want to make sure we're following some basic tenets and physics involved. So what I've listed here are basically the 6 necessary components or ingredients that you need for tropical cyclone development. Now, normally tropical cyclones that are going to impact Canada are not going to develop near the Canadian coast. It's too cold. The sea surface temperatures in the north are too cold for development. Typically, we get development much further south, and it may either bypass the U.S. coastline and hit Nova Scotia, or sort of make a direct line to Nova Scotia like Hurricane Juan did. So we do want to make sure, though, that we are kind of considering some of these things. In particular, looking at things like atmospheric instability. Does the atmosphere, is it conducive for development? Is the environment near Canada conducive for the strength of storm that eventually we're going to use as this extreme disaster scenario? As an example, it's very, very, very difficult, and depending on who you ask, maybe impossible, to get a Cat 5 to make landfall here. And why is that? That's because the sea surface temperatures are so darn cold. And sea surface temperatures are basically where the tropical cyclones are getting their energy. So from that perspective, you have to be a little bit careful about sort of the intensities that we allow to, even in an extreme event, given the physical confines of the actual system itself. So here's the basic anatomy, and I want to of a tropical cyclone. I want to go through it briefly, just because eventually we're going to talk a little bit about changing some of these parameters. So I want the important parameters in the context of what makes a big event versus a small event. So I have a tropical cyclone here cut into sort of 3 different pieces, 2 from the side and 1 from the top. Typically, what we're concerned mostly about with tropical cyclone is the wind field. There is also tropical cyclone-induced flooding as well, but we're going to focus on the wind peril. And when you talk about the wind peril, normally what you're concerned about is something called Rmax, which is the radius of maximum winds. So there's a very specific wind profile that most hurricanes have in some degree of homogeny or not, and that's in the bottom left-hand corner. So the colors of this bottom left-hand figure, the warmer colors indicate higher wind speeds, stronger wind speeds, and the cooler ones indicate lesser wind speeds. And so what you see is basically starting from the very center, where it's deep blue, there's really not a whole lot going on. That's in the eye. You know, everyone's pretty familiar with the calmness of the eye. But then as you go out, you see an increase in wind speed all the way up until you get to a point away from the center called Rmax, the radius of maximum winds. That's where you see the highest amounts of wind. That's where you're going to see the highest amounts of damage. And then you can see the wind field basically falls off as you get further and further away from the cycle. Eventually, you can't really tell that you're in the storm at all. But the location of this Rmax, with respect to our exposure, obviously has a very large implications for what the total loss of that event is going to be. Because you put something like that over a large exposure, that's when you're going to start seeing these losses. What I've highlighted here in red is where that Rmax is on each of these diagrams. So this is actually a plane flying on the top right, is a plane flying through the eye itself. So this is called the eye wall. This is basically a towering clouds here. And so the strongest wind speeds would actually be just on the edge of that eye wall here. And then the same thing, where basically everywhere where you see that red line, that's sort of the area that we're concerned about. And so we'll move this area around when we talk about the event to try and maximize our damage.
That's a very quick question. What's the typical radius of that?
It varies depending on where you're at, especially up in Canada when things with these. Actually, give me 1 second. I have a slide later, and then we'll talk about it. Yeah, thanks. Okay, so the Rmax is very important. Here's a couple other interesting things that are kind of go into what makes an event more or less damaging. Have 6 basically characteristics of events that you can modify or change based off of how much severity you're looking for. Intensity we just talked about. Basically that's the wind speed itself and the location of this Rmax. The other thing that you'll see if you look closely at this bottom left-hand corner is that cyclone wind fields do normally, not all the time, but normally have a pretty high degree of asymmetry. Typically on the right side of the storm, as it's going forward, you're going to see increased wind speeds, and that's because as the storm's moving forward, you have the storm relative wind speeds, and then you're adding to that the propagation speed. And so on the right side, that's where those 2 things line up. On the left side, those things are going in opposite directions, and so you have lesser wind speeds there. So you can mess with this asymmetry a bit. Something called the angle of attack. This is basically the angle at which the cyclone is going to make landfall to the coast. This is important because, as you can imagine, when you have wind speeds that are normal to an exposure, you're sort of going to get the biggest hit. You're basically going straight into it. Whereas if you're sort of making a glancing blow at it, perhaps the damage won't be quite as severe because it's not sort of taking the full brunt of the wind field. Landfall location is probably goes without saying. Depending on where this makes landfall, you're going to get more or less loss. Forward speed, again, that contributes to this right side asymmetry. The faster the cyclone is moving, the higher the wind speeds are going to be on the right side. However, it's sort of a double, the faster the forward speed, the less time the cyclone spends over one particular area. So this is one of the unique things about tropical cyclone is there is a significant duration component. So if you have a really slowly moving cyclone, even at the same wind speed, it's going to do more damage than a cyclone that's moving a lot faster. And that's because there is some sort of basically duration at which things start to fail. And prior to that, perhaps they might be able to survive. So we also want to consider forward speed and then indirectly via forward speed duration. I also have up here what in case someone's not familiar with it, the system that we use to classify tropical cyclones and hurricanes. It's called the Saffir-Simpson scale. It's actually classified by wind speed. You can see here it starts in tropical storm and goes from Category 1 through Category 5, being the most intense cyclones. Those are reaching speeds of 252 kilometers per hour or greater. These Cat 5 cyclones here are the ones where we could get into a lengthy debate as to whether or not these would ever be possible up in Nova Scotia. Okay, so sort of coming back to this idea of the dimension of RMAX, it's actually sort of a unique part of the Canadian domain is that as these cyclones are going further north, they're undergoing something called the extratropical transition. So without getting into like too much detail, the basic idea is initially when the storm starts, it has really warm air at the center of the storm that's sort of getting that from the sea surface temperatures. As it goes north, it basically sort of modifies the storm flow such that it sort of exchanges air around, and eventually the center of the storm actually ends up being a cold core system. So there's a warm core system, which tropical systems are warm core systems, and then extratropical cyclones, winter storms, are cold core systems. And tropical cyclones will transition into extratropical cyclones eventually. When they're doing that, it actually really modifies sort of the structure of the wind field and of the cyclone. One, it becomes significantly more asymmetric. So even though we have right-side asymmetry in the wind fields, hurricanes are pretty much symmetrical radially speaking around sort of the entire wind field with the exception of the right-side mass. Extratropical cyclones, on the other hand, highly asymmetrical. They actually look more like commas. So hurricanes look kind of like donuts. Extratropical cyclones look like commas. And so that's one thing, is it starts to become more asymmetric. And then the other thing, in the process of doing that, you start to see an expansion of the radius of maximum winds. Now, in general, because it's colder, the winds are going to be weaker. So as it's going further north and getting away from the warm waters, the cyclone is weakening in intensity, but it's also becoming much, much larger. And so now what you tend to get in Canada is not necessarily these really, really intense kind of small locations where you get lots of catastrophic damage. What you'll see is a larger area of maybe lower levels of damage. So in answer to your question about how this, the spatial extent of these RMAXs, it depends on where it's at from a latitude perspective, but 40 to 80 kilometers thereabouts. Depending on how far it's transitioned into the extratropics, then it can get quite large. Okay, so we've considered the meteorology a little bit. We know obviously we need sea surface temperatures. We know we're probably focusing on Atlantic Canada, maritime Canada. We're going to move on to step 2, which is looking at the exposure. So what I have here is what AIR calls the Canadian IED, the Industry Exposure Database. But basically, it's the total insured value of all the properties in Canada using a couple of different sources. And I have it graded here. This is actually on kind of a exponential or logarithmic scale. So you see lots of green, but in reality, most of the exposure is only focused in sort of in pockets and areas. It's not quite as widespread as it looks here. So we know sort of the area where we're interested in is over here on sort of the coast. We can zoom in a little bit and get a better idea as to where maybe we can do the most damage, because it's pretty likely that we can make landfall pretty much anywhere in here. We'll talk a little bit later about what the historical landfall distribution looks like. But if we kind of zoom in here, here's that same exposure. Now, because this is sort of spread out too far, it's difficult to really tell what's the worst place we can get. So I'm going to regrid this actually. So all I'm going to do is coarsen it and sum it up into big boxes. So I'm going to do half-degree boxes by just summing up all the exposure under each of the boxes. And then I'm going to threshold it. And so I'm going to throw out all the really small stuff. And I just want to see where is this exposure really, really located here. And those of you familiar with the domain probably already know where it's at. It's right here. It's basically Halifax. And so pretty much all this other green goes away after you threshold the lower levels of exposure aggregations. And so what this shows us then is that when we decide to do these events, we're probably going to set up the hurricane such that the RMAX is going to be somewhere near Halifax here, which makes sense from what you might expect. So that's what gives us an idea of where this location might end up being. Now, that being said, there's lots of different ways that you can affect this particular point. I've just randomly drawn sort of 3 very typical hurricane tracks that we might see from history, and it's a little unclear exactly which one does the most damage, but any of these are sort of an equally likely, equally probable type of track. So we're just going to choose one. And so I'm going to choose this, basically the one that's further south here, that basically makes landfall on the far south end of the coast and goes basically due north. This is actually very similar to the track that you saw in Hurricane Juan, that kind of basically due north almost. And so it's sort of a mix between that and a few of the other historical events. So now that we've sort of set that up, we do want to sort of look, okay, does this make sense with what we experienced historically? So what I have on the top left, these are the historical hurricane tracks. So these are all the hurricanes or tropical cyclones, that have impacted the Canadian domain in some way or the other. I have highlighted here a couple of specific ones, but the idea is just to kind of see how the general track works, which is basically diving in towards the coast and then recurving back as it goes further north. So our track is mildly consistent with that. This is what's called a loss cost. This is basically just showing from an AIR view where is the highest risk in terms of the hazard. So where are we most likely to see hurricanes make landfall? The darker areas indicate higher areas of risk. You can see somewhat uniform, a little bit higher risk in some of these areas here. But in general, we got the right area, right? And then finally, this is the historical landfall count. So what we do in our models, we actually break up the coastline into a series of coastline segments. And we basically track how many times an eye basically goes across one of these segments. And so you can see the area that we're interested in, which is on the far left here. You can't see it too well on the screen, maybe you can see it better on the computers, but it looks to me that we're somewhere between 5 to 13 landfalls between 1900 and 2012. If you look throughout the entire domain, that's actually probably the highest frequency. So I think overall, we've made some pretty good choices here. The question just now is, what's going to happen to the losses when we create an event consistent with these parameters? And so here's the final footprint hurricane scenario. The colors here are the wind speeds. The darker colors are higher wind speeds. The greener colors are lighter ones. You'll see some transitions. As an example, as you go from land to ocean, you see a transition at the coast because of the friction. On land is significantly higher, so we see higher wind speeds just off the coast here. I'll tell you that this is a Cat 4 hurricane. We have never had a Cat 3 hurricane make actual landfall in Canada yet, but Cat 4 is not outside of the realm of possibility. So we haven't gone all the way to the extreme, but something that definitely will take a while to get here. And then as you can see, I sort of arranged the wind field here so that this radius of maximum winds, which is this orange band over Nova Scotia, actually is sort of near the Halifax area. You're going to have to wait for the losses until later. It's the cliffhanger. So that's our tropical cyclone risk. So we have, and actually I've named it here, it's sort of the Halifax Howler. So I thought maybe it's sort of like a insurance horror movie almost. So the Halifax Howler. Okay, so that's tropical cyclone. All right, extratropical cyclone. So extratropical cyclones, I'll use this interchangeably with winter storms, low pressure centers. These are basically what you're seeing, your wind, your snow, your ice storms that are occurring in the wintertime. These are extratropical cyclones. So the perils we're concerned about here, Arctic temperatures, freezing rain, which is something that's unique in the model for Canada. Of course, we have wind and frozen precipitation, so that would be like snow and sleet building up on roofs. Now, in my experience, when we actually just built a model for Canada, and when you go through and you sort of look at the types of events that tend to cause the largest losses that actually are in the tail, it's almost always, except for, well, at least on the East Coast, the eastern provinces, almost always an ice storm. Because in general, the people in Canada, the buildings in Canada, they're used to being in Canada. And so it's not that warm, so they're built pretty well insulated. They're used to seeing snow loads of a certain type. We don't tend to get these really big snow and freezing temperature events. But what we do see is big events for freezing rain, because we start to see significantly higher loads than any other time in the wintertime, because the freezing rain is so sticky, because it starts to accumulate on the things on the power grid. So we're going to focus actually on the freezing rain. Everyone probably knows what it is, but just in case you don't, freezing rain literally is rain that hits the surface and then freezes as a sheet of ice. There's actually a special sort of atmospheric conditions that allows this to happen, and I'll show you here in the next slide. But the basic idea is that this is falling as liquid, supercooled liquid precipitation, and then when it hits the ground, which has typically in the wintertime sub-freezing temperatures, it'll flash freeze onto whatever object it happens to hit. And so if you have this around for a long enough time, you can actually start to accumulate pretty significant radial ice accumulations. And so we'll talk about the 98 storm here in a second and what that tells us about what's possible in this region in terms of ice accumulations. Biggest concern here is trees, trees that are overhanging structures, power lines, the power transmission system in 98. This was a big issue. The transmission system went down. This is why they were out of power for about a month in some areas. So we want to consider things like that, infrastructure, road safety, of course agriculture as well. But mostly we're going to be concerned about the power outage and freezing pipes because now the heat's off. So I mentioned there's sort of special considerations or special conditions in the atmosphere that this forms. I just wanted to sort of show you what that's like. Basically, in the atmosphere in the wintertime, what I'm showing you here, this red line in the middle of this diagram is the temperature of the atmosphere as you go up in the atmosphere. So height up this way, red line, the temperature. The freezing line is this black line that's at the bottom, or in the middle, excuse me. The way that we get freezing rain is basically you get some sort of really cold air at the surface that tends to be fairly shallow, sort of stacked underneath a fairly broad, warm layer aloft. Warm enough such that we actually get the precipitation to melt aloft into liquid precipitation and make it to the surface as some sort of supercooled liquid. So if this area here, this melting layer, is not big enough, then the precipitation will actually not melt fully. It'll stay sort of snow or graupel or some sort of frozen particle, and it'll accumulate on the ground like snow. If this surface layer here is too cold, then even if it melts in this melting layer, it'll still freeze again before it hits the ground. So it's sort of a very fine, delicate balance between the warm layer and this cold layer that results in these types of events. So I have a diagram here that just sort of shows here, you see the diagram before is a freezing rain event. The diagram now on the left would be a snow event. So you can see like the big difference here is the relative depth and strength of the warm and the cold pool here. Okay, so that gives us some ideas to the meteorology. Now, where do those things occur in Canada? Well, it's basically Ontario, Quebec is sort of the ice storm central of the Canadian continent. And so let's take a look at some of the exposure in that area. It is basically aggregated into areas where you might expect. So here's where we are right now. So here's Toronto. You can see Quebec City all the way at the top. Montreal there as well. So you can see we kind of have a couple pockets here that are prime candidates for some sort of an event that might sort of shock the industry. We can, again, regrid it to get a little bit better idea as to where is the worst location that can happen. Well, probably not a surprise to anyone here, is basically Toronto. And so we're going to actually focus on the Toronto area now in terms of what types of losses might we see if we saw a really significant Toronto ice storm versus what we saw in Montreal. So here is looking at some of the historical experience. Is it realistic to put an ice storm here in Toronto? Well, the easy answer is yes. Yes, it is. What I'm showing you on the left side here is the average, the median number of freezing rain hours, of the number of hours where freezing rain is occurring in a year. And you can see basically, as we talked earlier, basically this eastern part of Canada is really where we're seeing the highest degrees of accumulation. We don't see nearly as much accumulation here in Toronto, so this storm is going to be more extreme than it is compared to if this were to occur where it actually occurred, which is in the Montreal, Quebec area. They tend to get more freezing precipitation, freezing rain there because of some interesting cold air damming effects, which we won't get into. But the idea here is that it's definitely not outside of the realm of possibilities. Here's a list of some significant events going back to the 60s. There's more than this, but just sort of a sampling of events. You can see the typical ice accumulations that we see. And so you can see the 98 storm here, we actually saw ice accumulations, well, this is total freezing rain accumulations of 100 millimeters or more, which does a lot of damage. Yes?
You talk about this for some scale to describe the strength of hurricane. There's some sort of or some way of describing that 100 really stands out.
Yeah. So one, I'll show you the return periods here in a second. There is a scale that is used in the U.S. that we extended into Canada to use in the model when we developed it. It's called the Sperry-Pilz Ice Accumulation Index. Because one of the things we haven't talked about is that the damage for ice storms is not just a function of the ice accumulation, it's also the accompanying wind speed. Because you get significant wind loads on these radial ice accumulations. And so that index was originally sort of built to be like a Saffir-Simpson or like the ES scale for tornadoes. where it goes sort of 1 through 5, and it's a function of wind speed and ice accumulation. So there is some sort of classification there, but I'll also show you the return periods for the ice accumulations as well. It does stick out there, though, doesn't it? Okay, so here's the actual event itself. This is what we're going to use as a basis for the extreme event that we're going to create now in Toronto. So these darker colors you see here, this is those areas of 100 millimeter accumulations. The lighter areas where most of the areas being covered is 80 millimeter accumulations. That's both the US and Canada in the original event. Thankfully, you can see this could have been a lot worse. I mean, we're not going to get into this right now, but you can see how close this 100 millimeter contour is to the actual city of Montreal right up in there. Now, the power grid, unfortunately, is distributed. Actually, one main line falls right there, right in the middle of the 100 millimeter accumulation. So this was one of the main problems with the loss of this main line. But even in the event that we had, we could have shifted it around and probably seen even bigger losses than what we saw in 98. But now we're going to do one step better and move that to Toronto. Or better, I guess that depends on your view. Yeah. So just an overview of what happened actually in 98. So you can kind of imagine what happens when it comes to Toronto. I mentioned 100 millimeter of ice accumulation. That's about the size of a steam whistle can for those of you here in Toronto, the diameter. 1.5 billion in 98, as I mentioned before. That trends to about 3 billion if you do a flat trending, 2 billion if you account for changes in the infrastructure. Lost over 1,000 high-power transmission lines. These are those big, tall towers that actually is fairly unique to Canada given the voltage that runs across them. It's one of the only places in the world that has such high voltage lines. Over 30,000 utility poles. Those are those wooden poles that go residentially. So the distribution system completely shot. 4.7 million people at one point without power. That's 16% of all Canadians at the time. So more than 1 in 10 basically had no power. And some of them without a month. And interesting fact, at the time it was the largest deployment of the Canadian military since the Korean War to do the recuperation effort. So really, really quite the event. Yeah.
You mentioned unique that we have transmission towers.
Yeah.
That's all I really know. So if you're carrying that kind of power, what's the alternative to a transmission?
So it's not that the transmission towers that are unique, it's the voltages on the transmission towers. So in other places, they would break up the transmission of that power into maybe separate lines. Here, we're doing it because you have the hydropower, basically one big line, well, a few big lines now. But the unique part is sort of the concentration of that delivery through those kind of 5, 6 main lines that go through the Montreal area. Yeah, they've done some things now to improve that system to have greater redundancy, and so that sort of goes into the calculation of if 98 were to happen again today in the locations that happened, what would the loss look like? We estimate to be less than if you were to just trend it based off of exposure growth. Yeah.
Now, was that the power from James Bay going down to New York, or was that going into the Montreal area, or was it both?
And don't quote me entirely on this, my understanding is that it's both. There are a couple of different systems that connect to that transmission system. I don't have the diagram here, I actually had it in a different presentation to show you, but it does sort of go down into New York and then across sort of the province. The main lines that went down were basically the ones that are surrounding Montreal. So I think at the time, Montreal had either 3 or 4 main entrance points for the grid, and basically 3 of those 4 lines went down. So
my understanding, the high voltages are due to the fact they're trying to get it down.
That's right. Yeah, it's because of the distances they have to travel.
They have to move it into Montreal itself. They step it down.
That's right. That's right. But those high voltage lines are the ones that failed. So that was the issue. Is that it's like kind of the main lines really came down at that time. So hopefully, if it occurred again today, it wouldn't be nearly as bad. But still, 100 millimeters of ice is very thick and heavy on those lines. Okay. So we do want to check, before we move this to Montreal, kind of getting to your question about return period. All right, so if we make 100 millimeter precipitation in Toronto, how extreme is that really? Are we talking 1,000 years, 1,000,000 year return period? How, are we really being reasonable with that? And so what I pulled here is the 200-year return period and the 400-year return period for what's called the radial equivalent ice thickness. And so that's basically if you take the ice and you distribute it uniformly around a wire, how thick would the radius be? And so here's the equation to basically convert total accumulation into radial equivalent. So as an example, the 98 storm has a radial equivalent of about 35 millimeters. So you just basically 100 and divide by the density and by pi. So if you look at the original location, 35 millimeters, So basically, now I only have these return periods for the U.S., but you can sort of extend them across the border into Canada. The area right in here where it actually originally fell, so this puts the 98 storm in the Montreal area, probably around 200 to 225 year return period. You move that to the Toronto area, you can see it does end up becoming a significantly more severe storm. You can see the 200 year in Toronto is about 30 millimeters, 400 year about 40 millimeters. So in Toronto, this return period for just the ice accumulation itself, somewhere between the 200 to 400 year return period. Now, that says nothing about the size of the storm, because it's not just a single accumulation. One of the things about the storm was that it was actually a fairly large area of very, very thick ice. So the actual return period of the entire storm itself, if you include intensity and size, is going to be higher. It's going to be significantly more severe than 200 to 400 years, because you have to sort of incorporate everything along with it. But at least the overall accumulation's 200 to 400 years. Okay, so I think we sort of decided it's not so unreasonable, definitely extreme, not out of the realm of possibility. Hopefully everyone agrees. So we'll take 98 then, and we'll move it to Toronto. So there it is. So this is the Toronto ice storm. I couldn't think of a really quippy name for it here. So if anyone on the webinar has an idea, you can chat it in, and we'll name it for you. So there it is. So this is the 98 extreme disaster scenario for Toronto. And just a reference that all of you will probably know, 35 millimeters radial equivalent, approximately the size of a hockey puck, thereabouts. Hockey pucks are a little bit bigger. And actually, this is one thing I found out, is that apparently it varies. The standard size of a hockey puck, plus or minus 4 millimeters. Is that right? Okay, nobody knows. All right, approximately hockey puck, just to give you a visual representation of what's going on. All right, so tropical cyclone, winter storm, still got you on the edge, hopefully. One last one, severe thunderstorm, and then we'll have the big reveal at the end as to the losses and some discussion about those losses. Severe thunderstorm, what we're talking about here, straight line wind, hail, literally pieces of ice falling from the sky. People in Calgary, very familiar. And tornado, these are rotating columns of air at the ground, winds in excess of 200 miles per hour. You all just had your first, what's called an EF5 tornado, which is the most intense category of tornado recently. I think that was the first reported one. I think it was 2007, I want to think. 2009. July magnitude. Yep.
EF is the new scale, right?
EF is the new scale. That's right. So just briefly, there used to be a scale called the Fujita scale, or the F scale. This was something that was established by Ted Fujita at the University of Chicago when he started his work back in 1974. It wasn't completely well calibrated necessarily. It was based off of the fastest quarter-mile wind speed, which is sort of a somewhat unique usage of wind speed. There was a movement recently to sort of standardize this scale using damage indicators, and that is sort of where we go between the F and the EF scale. So recently, they basically went through and decided, okay, if you have a house that loses its roof, it's X miles per hour. If it loses its roof and all of its exterior walls, it's Y miles per hour. And it basically has a set of those damage indicators to help basically people that go out and do storm surveys to accurately sort of estimate what the wind speed at that location might have been. So we use the EF scale now based off of these damage indicators. All right, so step one, right? Consider the meteorology. Here it is, ingredients. So there's three basic things you need for severe thunderstorms. Instability, so this is the basically whether or not air wants to rise in the atmosphere. Something called vertical wind shear, which is the change in wind speed with height. So one of the unique things about severe thunderstorms that tends to differentiate them from non-severe thunderstorms is that oftentimes they have a significant component of rotation. They're called supercell thunderstorms. It needs to get that rotation from someplace, and it gets that from environmental wind shear. So when the wind increases with height, it can use that and turn it into rotation that it can later use for tornado genesis. And then finally, we need some source of lift. So we can have all of these parameters together. It can be really, really unstable, lots of great wind shear, but there's always sort of a cap on the atmosphere, and we need something to sort of, as a spark, to sort of start the event off. Once it sort of gives it its initial push, then the environment will take it from there. But we need some form of lift in order to get thunderstorms to actually occur. So the co-location of these three main parameters basically determines where in the domain you're going to see severe thunderstorms. So if we look in the Canadian domain, where do we typically see all of these parameters? Well, I'm going to show you, this is a parameter called CAPE, convective available potential energy. It's a measure of instability, where you see high values of CAPE you typically have more unstable air. So we look at this, okay, yeah, all right, yeah, the US has got lots of it, whatever. We look at Canada, though, and you can see, maybe predictably so, you sort of see this sort of swath of higher tape kind of going into the prairies and through basically right into the Calgary area. So instability-wise, typically we focus on the prairies here, but you can see there's also potential in other places as well. We do get severe thunderstorms in the eastern provinces as well. But this sort of shows you where that parameter is located. Now we need some sort of wind shear. One of the things we look at when we're determining wind shear is something called the jet. The jet is basically an area of high wind speeds aloft, and typically it depends on a couple of different jets, depending whether you're mid or the upper level jet. But basically, if you have really, really high wind speeds aloft, then that probably means that you saw increases in wind speeds with height, which is what we're looking for. So the location of this jet, especially during the summertime, sort of indicates where you're going to see decent amounts of shear in the Canadian domain. So this orange line you see here, this is the location, the average location of the summertime jet. And so, again, you can kind of see the picture is becoming clearer. The prairie is really not a great place to be if you don't like severe thunderstorms or hail. And then finally, the last component, lift, right? One of the things that's sort of somewhat unique about the prairies in Alberta is its proximity to the Rocky Mountains here. So the Rocky Mountains provide a couple different mechanisms that the environment can use to initiate severe thunderstorms. One of the things it can do is called upsloped flow. So basically, the wind speed that hits the mountains, well, because the mountains are there, it has to go someplace. It goes up. So then once you start moving it up, that's the spark you need. Then it'll sort of initiate on the mountain ranges and then propagate back to the east. The other thing that can happen is things like what's called differential heating. Because of the different slopes, the different land covers, you get hot air over there, cold air over here. When you get that sort of differential heating, that can also be a source of some sort of environmental lift as well. So really, what you see is those three ingredients really combine into this area here in the prairies, into Alberta, going down through Saskatchewan. Also, some combination of that here in the Toronto area as well. But really the focus is here on the prairies. So, so we looked at the meteorology, we looked at the exposure. Here it is, again, it's kind of spread over everywhere, so we'll regrid it and really focus in on an area that is sort of the hotbed that everyone likes to talk about. That would be Calgary. Here it is a high res. This is a 1 kilometer resolution. Total insured value, you can see pretty clearly where we're going to be going for this, but just in case you can't see it, here it is. After it's been thresholded, basically all the exposures are right there. Of course, there's exposure to the north too, but the further north you go, the less the severe thunderstorm activity because it starts to get kind of cold. The moisture doesn't make it quite as far. Okay, so is that consistent with what we see in the literature? So actually, I think this actually might be from an ICLR presentation. So that I think maybe Glenn gave not too long ago I was at. This is showing on the right side the average number of hail days in Canada. Again, as expected, the prairies is sort of the hotbed, Calgary being the bullseye really of where we're seeing it. Population related, you have to be a little bit careful, but you can see both the environment and sort of the ops are showing you the same story. This is work from Environment Canada. This is David Sills' work, looking at all of the tornadoes from 1980 2009, confirmed and probable because it's just a little bit too sparse from a population perspective to know for sure. But again, you can see basically the prairies in Alberta, but a pretty decent secondary max here. We won't talk about the one here in Toronto. We're going to really focus on Calgary, but really a large potential for events here. It's really just a matter of time. Speaking of events that can happen in a matter of time, all I did was go back and look again at an ICLR presentation that had a great list of recent hailstorm events of significant value. And so I pulled just the ones from the 2000 onward to look at what types of events have we seen in this area already. We want our extreme event to actually be bigger than what we've already seen. And you can see a handful of really quite severe events, especially recently. You can see 2010, 2012, 2014, all $500 million or more, just in a single event alone. One of the things that's not on here because it didn't make the date cutoff, 1991, which had really big hail, but also, I believe, somewhere in the 500 million, maybe a little bit less, depending on how you trend it. But you can see potential clearly here. I have here on the top left, this is the outline of the Calgary hailstorm from 2010. Most of the reports that I found in 2010 actually talked about golf ball size hail, so that's about 1.75 inches. I think that's 40 to 50 millimeters thereabouts. but there was at least one source that indicated up to baseball-sized hail, but just not right in Calgary. Here's this is damage from the 2012 event. The largest hail reported here, between 50 and 60 millimeters. Right here, you can't see it too well on the screen, but that is a golf ball on the far left, and everything else in there is hail. And so you can kind of see the relative size of that hail, golf ball size and bigger. So that's probably pushing upwards of 2 inches in terms of hail sizes. And just to let you know, I want to show you, in 1991, the largest hailstones reported, now thankfully this storm did not hit right in the center of town, largest stones reported 100 millimeters. 100 millimeters. So this is not from that storm, let me be clear. This is from some storm in Oklahoma, but I wanted to show you what 100 millimeter hail looks like. And that is even a little bit small. When I measured my hands, it should be a little bit bigger on our hands here. But this is what's coming from the sky in 1991. So imagine what that does when you move it over downtown Calgary. So just think about that before we get to the big reveal.
Then the other factor is the density of the stone and the speed at which...
Yeah, that's right. And actually in 2010, one of the indications is that this hail was actually very hard. So hail does vary in density quite a bit depending on the storm. These stones here were actually hitting the ground and jumping upwards of 3 meters in the air. And so that's a pretty dense hail. Typically the average hail density is around 0.9 grams per where water would be 1. But you're right, the density of hail. The other thing that we haven't talked about is the accompanying wind speed as well. If you have significant horizontal components, you're going to get damage to your roof and your building cladding, which can be significant if you have high wind speeds. Okay, so I'm convinced, hopefully you're convinced, I think we can have a pretty big event here in Calgary. And I think it can be a lot bigger than what we've seen before. I think we've really just been lucky. So here's my proposed extreme disaster scenario for severe thunderstorm. Here's Calgary right here. We can see the storm initiates off the mountains, basically propagates eastward. Very, very, very similar to what happened in 2010, just a little bit further to the south in terms of the center part of the storm. Big difference here is that I'm going to let 4-inch hail fall all over Calgary. So we'll take a look and see what does that mean for the city in terms of losses. Okay, so you've made it to the end. Hopefully you're all still awake and you're ready to see the losses, but I wanted to do the overview. Here are the 3 extreme disaster scenarios. So we have the Halifax Howler, the Toronto ice storm, and the, oh, did I give this one a name? Let's see. The Calgary Hailer. Calgary Hailer.
Somebody online recommended the Toronto Tumblr for that too.
Ah, the Toronto Tumblr. I like that. I like that. Next. Yeah, okay, so the Calgary Hailer. So here are the 3 100-millimeter hail here, 100-millimeter ice accumulations here, Cat 4 strength hurricanes here. That is a bad year in Canada, okay? That is a bad year in Canada. So what do the losses look like? You've waited long enough. Let me show them to you now. So here are our 3 EDS events. And for our Halifax Howler, the model estimates a loss upwards of $30 billion.
Insurance loss.
Insured loss. Insured loss, gross, after terms and conditions, $32.5 billion. Now, keep in mind, that is significantly bigger than anything we've seen in this area, but it's also a Cat 4, which is at least 1 category higher than anything we've ever seen make landfall. So again, the whole idea here was, let's come up with something that's meteorologically plausible, but really, really unlikely. So $32, $33 billion. The Toronto Tumblr, as it is now called, $26.2 billion. So the original event, again, $1.5 billion in Quebec. Significantly more exposure in Toronto. There's about $3.5 trillion of exposure in Toronto and the surrounding areas. And now we're covering that entire area with 100 to 80 millimeters of ice accumulation. You can imagine significant loss there. And then finally, actually maybe I should have put it first because it's a little anticlimactic. The Calgary hailstorm, maybe perhaps a little more reasonable, $13.6 billion. Now, that is still significantly bigger than any other hailstorm we've ever had here. I think the biggest one is in the upper 500s, if I remember correctly. But very much in the realm of possibilities, I think, given the meteorology and the fact that we just haven't seen a direct hit right on the city before, especially not a 4-inch hail. But, well, actually, what time is it? I don't want to run too far into it.
It is 10 to 11.
10 to 11. What time are we supposed to be done? 11:30?
11:30.
Oh, good. So the question is this the end of the story? And the fact that I have at least 10 minutes left means no, it's not. So I sort of came up with these events. We did look at the meteorology, but who's to say these really are the biggest events we can have, right? There's a lot of sensitivity involved, especially in location. You shift the Calgary hailer here to the south, to the north, nothing happens in terms of loss, right? And so one of the important things, I think, when you look at these events is also to understand the sensitivities as well. Yes, these are really big numbers. Yes, these are very, very extreme events. But let's try and understand a little bit how sensitive are these numbers to small changes in the location of the intensity. Maybe that gives us a better idea of something that's maybe a more, I won't call it a more reasonable loss number, but perhaps something more of what you might expect to see in the near term. So we're going to do something called perturb the events. We're going to basically shift it in space and in intensity. We're going to make it stronger or weaker. The way that, in case you're unfamiliar with the terminology, perturbation just means basically small little changes. The idea here is that there are certain changes you're going to make that really aren't going to make much of a difference. You're going to push it a little bit, and so you say, okay, that's fine. Here's your loss number. It's about the same as what you had before. Other perturbations, because of how nonlinear some of these things can be, especially in the location adjustments, are going to be highly unstable. And so that means just a little nudge one direction can really send the losses through the roof, more through the roof than they already are. And then finally, you have something that's sort of more neutral. You sort of push it, and it changes with, it's sort of proportional to the changes you're making. You know, something that is not as scary as something that is more on the unstable side. So we're going to call this low sensitivity. So that would be when you make changes that really don't change the losses all that much. High sensitivity, this would be things we start to see things like exponential changes with your loss, with your perturbation. And then we'll call proportional sensitivity. So this would be, you know, I increase by 10%, my loss increases by 10%. Not nearly as exciting as some of the high sensitivity effects. So we'll look at these events a little bit here. So let's look at the Halifax howler. And what we're doing here is looking at track perturbation. So what I've done is instead of having a big landfall where the actual event was, what I've done is actually shifted it, you know, like 20 kilometers up and down the coast, back and forth. And I did it with 9 different tracks. So you can see here what the distribution of those losses look like, depending on where those tracks are located. Again, basically these are changing with distance to Halifax, and the distance between the RMAX and where Halifax is located. That's a really driving factor here. But one of the nice things, at least, not really an exponential change here. I would call it fairly moderate difference in terms of the track. Now, of course, if you push the track really far, you can get it completely away from anything. Then, you know, then your losses are going to come all the way down, and there'll be nothing here. But these are small perturbations around the initial EDS that we want to look at. So here I would call sensitivity of these hurricanes, of that particular hurricane, to location adjustments fairly moderate. Nothing to get too excited about. Here is something to get a little more excited about, and that would be the intensity distribution. So in our model, we model hurricanes by central pressure. Central pressure are related to sort of the maximum wind speed. So just in general, the lower your central pressure, the higher your maximum wind speeds are, okay, in general. What you see here is that as we go from the base intensity, which by the way was 936 millibars, this was the initial storm, to something all the way down to 908, which is a really deep low, you see a somewhat dramatic increase in losses. So that original event was, let's see, actually I think the original was 926, excuse me. 926.87, it was around 36 billion, I think is what we decided. You can see it goes all the way up to 37 billion just with a 28 millibar drop in pressure. Now, that's actually a pretty significant drop. This is part of the problem, is that going from 926 to 908, that is not an insignificant perturbation. So part of this is because we're really pushing the model hard. In fact, we're probably approaching somewhat unrealistic wind speeds here in terms of making this into a Cat 5. So keep that in mind. This is another, I think, important lesson, especially when you start to mess with some of these events, is that your initial event may look okay, but then when you do your perturbations, you may push it past the point where we're really sort of reasonable looking. So you want to keep that in mind. But you do see a pretty significant sensitivity, though, to the change in that central pressure. So that's something to keep in mind when you're dealing with these events, is how sensitive it can be to what you've defined as the central pressure.
Have you went up the range? Have you done, or down? Have you done Cat 3, Cat 2?
So that would be like these guys here. So the original one was like somewhere in here, and so there's 2 of them here that are weaker than what the initial ones were. So you can see. So this is probably, you know, I have to go back and look at exactly what this wind speed is. But you can see the loss is a little bit more manageable at about $11 billion here at the sort of the weakest event that you've got. Still, more significant than anything we've seen here, and that's because we've got a direct hit on Halifax, right? I mean, it's really going to be, you shift that away from Halifax, you're not going to see nearly that level of loss. I think Hurricane Juan's loss was somewhere in the 200 million range thereabouts in 2004. I think that was the largest loss causing that we've seen so far. But there was also a Cat 2 at the time it made landfall. It was not a Cat 4, which is what we developed here for this extreme event. Okay, so why the dramatic difference in losses? Well, one of them, as you increase it, the wind speed goes up. The other thing that we haven't talked too much about, and I'm not going to talk too much because I'm not an engineer, but the damage curves that are used in the models are also fairly nonlinear. Oftentimes, so the damage curves, basically what they tell you is, given a wind speed, here's what the mean damage ratio is. So given a 150 mile per hour wind speed, on average, you're going to damage a building by 3%, something like that, okay? That average damage ratio is a nonlinear function of the intensity. Some of it is a function of exhaustion, so the duration itself, like I mentioned before, 150 mile per hour winds for 5 minutes versus for 20 minutes. There's a big difference in the loss that you get there. Also, one of the things that contributes to the nonlinearity here that I'm sure the folks here at ICLR are very familiar with is that certain mitigation measures fail at certain thresholds. So up to a certain point, you may have some sort of protection on your house that is effective in mitigating the damage, but at a certain point, even that will start to fail, depending on what it is you're looking at and which mitigation measures. And so there's some nonlinearity in it there, and that initially when you increase it, you're not going to see any increases, but when you get to the point where you're seeing failure of those mechanisms, then you may start to see more dramatic increases in loss. And then finally, there's something that called the secondary uncertainty. So I mentioned earlier, this curve gives you the average damage ratio. So the key word there is average. If you basically, if you go back and do a storm survey of a location that experiences a certain wind speed, what you'll see is that some of these houses are just gone, and some of them, lost a shingle or two, maybe part of the roof is gone. And so even within a block, you may see significant variations in the damage ratios themselves, even though they probably all experience the same wind speed. That's a function of building practices and whether or not you have mitigation measures. There's a lot of things that go into that. Yeah.
Building practices are a huge issue. There's actually a picture going back to Hurricane Andrew where you have one side of the street followed the building code, the other side of the street didn't. One side of the street, there's some damage. A little chunks of the roof are gone, that sort of thing. The other side of the street looks like 3 little pigs.
Just gone. Yeah. And we actually do try to account for that in the model. The change in enforcement and the building codes, regionally speaking, when we have that information. So that's actually something that's implemented here, but you're right. I mean, sort of the application of those building codes, how well they're enforced and followed, can have a significant, effect on whether or not, houses survive these things. Anyway, so there's a combination of things. I guess the point I'm trying to make that make these losses nonlinear with the increase in wind speed. So mostly the point here is just be aware that this type of behavior can occur, and it may change depending on where you're at in your intensity. Yes.
So you do have data on code enforcement for Halifax that you?
Off the top of my head, I cannot tell you all the data they pulled. I know we have the National Building Code of Canada, so there's a lot of information in that. We've looked at how that has evolved and how those, to the best of our ability, how those are being implemented. I'd have to get a little bit more detailed information from the engineers to answer your questions fully. Okay. But we do have some of the information about the building codes and how it changes through the region.
Right.
Yeah. Mm-hmm. Okay, so be aware. High nonlinearity with intensity, especially at the kind of the middle levels here. All right, so that's hurricane. Let's look at the ice storm. This is actually pretty interesting. So what I've done here is I've really kicked the model very hard. And so you can see the maximum ice accumulations I put through the model, 130 millimeters. Okay, so that's a 30% increase in what is already a really big number. So you can see what I'm showing you here is the average loss over all of the spatial perturbations for that particular event. You can see we actually get losses upwards of $32 billion for something that has a 30% increase. This is actually a really good example of how your increase with intensity can be nonlinear depending on where you're already at in the curve. You can see initially it's actually pretty linear. So going from 100 millimeters all the way up to about 110 millimeters, that's a pretty linear trend there in terms of how the loss is changing when you increase your intensity. And then all of a sudden you see this big break here. And that's because, again, these damage functions, they have different levels of nonlinearity depending on where you're at. You can see initially they're pretty flat. Then you get into some of this part of the curve where you see a big shoot upwards. you might start seeing significantly more nonlinearity depending on where you're at. So that's an important thing to note, is that it's really dependent on your intensity here. And then finally, looking at some of the perturbations for the Calgary hailer. Oh, sorry, that was the Toronto Tumbler. Now we have the Calgary hailer. And so what I've shown here is actually kind of to your suggestion about the hurricanes. I've actually done the same thing for the hailstorms. So instead of going upwards, I did go backwards just to see, okay, what does the model look like? Maybe you don't think 100 millimeters is reasonable, but maybe 70, 64, just to see how does the model behave. What you see is you actually do get significant events going all the way back into, like we know already, that these events where we got 500 million, 500 million, 550 million, probably on the order of 1.75 to 2.25 inches mass size, depending on the reliability of the actual observations themselves. That puts us basically in these two categories here. You can see, according to our model at least, the probabilities are that those events probably were closer to 57 millimeters in terms of the maximum hail size. So that gets you within the range of what we expect. You can see the average is 292, but you do have a maximum here, 476, medium 330. This is basically in the range of those losses that we see. Anything bigger than that, we start to get into the billions, and we clearly weren't in the billions there. So what this is telling me, one, is that those events probably were somewhere in the 51 to 57, but it also tells me that even though the scary $9 billion number here, or 14 billion for the max, is quite large, even moderate decreases in the hail sizes can decrease that amount somewhat substantially, but still end up with events that are significantly higher than the 575, 595 million that we've seen max in that area already. And so here's just the bottom is just the bar plot of the stuff of the average from the top bar here, just to kind of see how that trends here. Be careful between 70 and 30. The 30 millimeter change, 64. Obviously, it's not in equal bins here. So just that big jump is not quite as big as it looks from the plot. So why do we see those types of changes? And we're coming into the end. I am actually a classically trained physicist, so I couldn't go through a presentation without looking at an equation in some form of physics. But I'll be nice to you. We'll go back to high school for most people, and we'll look at classic kinematics to explain why we see the sensitivity with hailstorms. So the basic idea is that the energy that the hailstorm delivers to a structure is basically the mass of the hailstone falling from the sky. It comes to some sort of velocity driven by gravity, and it hits the ground at a certain speed. And so, in the very basic sense, ignoring the fact that they're not really round and they have spikes and they rotate and do other crazy things, first order assumption, basically the energy that departs the building is the kinetic energy of the hailstone, which is, for those of you, of course, all remember, 1/2 mv squared. Great. Actually, it should be the change in kinetic energy is 1/2 mv squared, but that's getting into detail. Okay, so it's basically a function of mass and velocity. That makes sense. Mass is a function of density and volume. Velocity is a function of gravity, because this is the force acting on the hailstone, versus the drag, which is a function of basically the cross-sectional area. And so where these two meet, that's where you get your terminal velocity. So that's the speed that it's going when it hits the ground. Most of the stones are going at terminal velocity when they get to the ground. Okay, so let's think about it. Let's assume a sphere. They're not spheres, but let's assume they are. The volume, so we're looking at the mass, which is related to the volume. The volume is 4/3 pi r cubed, the volume of a sphere. Great. Now we can convert that though. R in radius and diameter, same thing, right? It's just that radius is 1/2 the diameter. So we can rewrite this 4/3 pi r cubed as 1/6 pi d cubed. Now, if you are falling asleep and you cannot follow, just look for the red letters. That is the important part. So the important here, d cubed, very important. All right. Now, let's make a couple more assumptions about drag and the way that stones fall. Here's a little bit of a tribute to either the Copa Americana or the European Cup, depending on which soccer matches you're watching lately. But basically, given the drag force of a sphere falling in the atmosphere, and assuming some sort of coefficient of friction, you can actually simplify all that crazy math down to say the terminal velocity is approximately 4.33 d to the 1/2. So that includes the density of hail and et cetera, et cetera. Again, an approximation, but it's red letters, good. D to the 1/2, perfect. D cubed, D to the 1/2. So here we are, we have mass proportional to D cubed, velocity proportional to D to the 1/2. We take it and put it into our equation here, 1/2 mv squared. And what do we get? So we get m, which is D cubed, V squared is d to the 1/2. That's d cubed times d to the 4th. So kinetic energy proportional to d to the 4th. So this sort of makes sense right now. When you have a 10% increase in your diameter, which, you know, when it for a 100 millimeter hailstone is only, what, 10 millimeters, you actually see that effect on the energy basically over and over and over again because it's really proportional to the cube here because of this volume component. And so this sort of explains why we see such a sensitivity to diameter changes, because it actually, you think you're only increasing it by 10%, but you're actually increasing the energy by significantly more. And so here's an example of what that means for perturbation. So as we go from pea-sized hail here to, I guess that looks close to 100 mass, probably like 80 millimeters, thereabouts, 80 to 85. What does that mean? So given a diameter, if you add 10% to it, it's 10.10 times the diameter to the 4th, you end up with, so a 10% increase in diameter actually ends up being a 1.5 increase, x increase in kinetic energy. Push that to the extreme. Let's say you take a 1-inch hailstone and make it a 4-inch hailstone like we did here. 4 to the 4th times the kinetic energy, a 256 increase. So even though we increase the diameter by 4, we actually increase the energy by orders of magnitude more. Makes sense now why we see such dramatic increases in the losses. So energy increases non-linearly with diameter, so that's one thing. And as we've already discussed with wind, the same thing goes with hail. Damage increases non-linearly with energy. Things like impact-resistant roof coverings typically fail around 2 inches thereabouts, sometimes even earlier, depending on when you got them and how long they were sitting on the shelf. And so up to 2 inches, not a whole lot going on there. After 2 inches, these things are getting destroyed. You're going to have to replace them. So a lot of non-linearity there. All right, so putting it all together, here are our extreme disaster scenarios that we went through. The Halifax Howler, the Toronto Tumbler, and the Calgary Hailer. This is just showing the sensitivity of that Calgary Hailer that we looked at earlier. And here are, again, the total losses just from the base scenarios, 32.5, 26.2, and 13.6 billion respectively. So just as a summary, what does this all mean for risk management? It's been a great little trip here, but what can we do in practice, or at least what should we take away from the presentation, what I want you to take away? One, I think this is really important. This goes back to basically the very first slide I presented, and that's every single generation, without a doubt, every single generation has a scenario that won't ever happen that happens. Every single one. So think about that when you look at these events, you go, okay, there's no chance and you know where this is going to happen. Just think back to Hurricane Andrew. Number two, robust risk management demands examination of these events. So even though, obviously, these are way out in the tail, very, very extreme events, we've sort of taken things and we've put them in the optimal location to cause the most amount of damage, they are still meteorologically plausible. So it's really important, especially given the levels of loss that we see when we have these events, that you at least consider them. I'm not saying include them in your pricing and try to file with these types of things, but I do think it's very important for you to be aware that these potentials are out there, and what would that mean if these events actually were to occur for you. Hopefully you saw, we can actually judge whether or not these events are plausible, meteorologically feasible by looking at some of the meteorology that goes into them and what we've seen before. I think, hopefully you agree, the events we came up with, not too much of a stretch. Maybe the Cat 4 in Nova Scotia is probably the biggest stretch, but I think it's all still generally consistent with the way the atmosphere works and the physics that sort of determine how damaging these events can be. And then finally, sort of summing up the last part of the presentation, I think it's really important to understand the sensitivity to some of these things. So when you get a loss result from a model and you go, oh my gosh, how is that possible? Think to yourself, go like, okay, well, but what if they got it wrong by 10% maybe? Maybe the intensities are overbaked just a little bit. Understanding what that means to your overall loss number, and the reverse, what if they underestimated it by 10%? I think it's sort of an essential part of a strategy that is sort of a full, all-encompassing risk management view of the marketplace. So with that, I'll throw up my contact information here. I'm sure we have, hopefully not too many questions, but maybe, that we've come through here. And so we'll take questions now. Thank you very much.
Great, yeah, thanks very much. We actually have not many questions online, so I'll open it up to the room first and give everybody who's signed up a couple of seconds to think about a question.
I've stunned them all with my loss numbers. Yes, go ahead.
Yes, I kind of dabbled in modeling a few years back, and I found that the main issue was not so much the meteorology, or the characteristics of the event itself, but relating that back to building damage. So I was just wondering, how granular is your building damage statistics? Did you basically take the previous storm's damage in total and then sort of scale it up? You were alluding to the fact that you were doing some work, with building codes and so on. I don't expect the details, but I was just wondering how granular you were and how detailed you sort of went into individual.
Sure. Yeah. So I can only speak for AIR, but it's generally, I think what we do is pretty well accepted. Lots of people do similar things. When we do validation and we do the development of the damage function, we actually look at the event at sort of multiple different scales. Typically, we start from the top down. And so the first thing you look at is we have some engineering judgment. You've got to come up with some damage functions. You say, okay, here's what the event total looks like. It comes out of the model. How'd I do? Because sometimes you have that breakdown by line of business. Sometimes you have it broken down by type. Then little by little, you start basically focusing in. So instead of doing industry-wide validation, now maybe you'll take specific companies that have a fairly large market share. And you'll actually look at location-level claims, some of these large, typically we actually do like a zip code level analysis first. And then we look at that, say, okay, we can make some adjustments here. Then we bring in the actual location level books. So we'll actually get books of business from reinsurers or from primary insurers that actually have the locations, the exact a lot of times it's incomplete, but the characteristics of that particular risk. How much did they pay out? We know approximately what the meteorology was. So we really do that validation on a very wide range of scales. The best we can do is we try to get as much detailed location level claims data in it as possible. Certain countries are better than others. Canada, as an example, a little bit more difficult to get data here than it is in the US. And so for the Canadian models, maybe there's a little bit less information that goes into, location level information that goes into those damage functions. At the same time, we can leverage some of the information in the US to help us out in Canada as well. If you're right across the border and you account for changes in the building code, which by the way, your building code is much better, and then you can still sort of get an idea, okay, how does a wood frame home behave given this type of input? So it's kind of on a whole bunch of different levels. Hopefully that kind of answers this question. Okay, good. Yeah.
Well, one question online. We've got a question from James. So how did your Toronto simulation match with the Christmas ice storm from 2013?
So that's the Toronto one in 2013, right? So we actually, interestingly enough, in the model that we put out into the market, 2013 is one of the historical events. And so one of the risks you run when you try and use 98 to come up with an ice storm damage function is that it's more extreme than anything you've ever seen. So you can really over-tune the model to that, and then all of a sudden you won't be able to produce losses in line with these smaller events. As it turns out, we actually ran 2013 through it, and I think the loss number ended up being somewhere between $200 and $300 million, which actually is right about what it happened to be. So we did try and make sure, kind of in line with the validation I just talked about, in addition to looking at claims of different sizes, we try to make sure we validate against events of different sizes as well. So the model actually performs pretty well for that event. Yeah.
In fact, date-wise, that event was right after our model came out, and we are waiting to see, let's see how the model performs, and it did pretty well. And just to come back a little bit on the engineering side, as we look at different types of buildings, we have very detailed engineering analysis of like three-story building, two-story building, what the building is made of. A lot of research is done at AIR, or the type of research output that we from organizations like ICLR and different agencies. So at a very detailed building-specific damage function-wise, it's quite up to date.
Thanks, Kunal. Yeah.
I really enjoyed that presentation.
Oh, good. I'm glad you liked it. Really hopefully it didn't scare you too much, right? Yeah.
Just something that's not available anywhere else.
Yeah.
Really impressive. Thank you. So one of the areas that helps me validate and accept these extreme numbers, I'm trying to think of what would these losses look like? Where do they show up? Mm-hmm. And you start off by talking about some of the big events internationally that surprised the insurance community and others. So the flooding in Thailand was one other example. And again, you've got rain happening on the other side of the world, and we had factories closing here.
Yeah.
Right? So it was very unusual. We had losses show up in places that people hadn't really thought through. So I'm going through these three scenarios and trying in my head, what is it that leads to the claims that you're
Level of loss.
describing?
Yeah.
So the most complicated one for me is probably the Calgary event.
Uh-huh.
So you were choosing to focus on the size of the stones, but you've got damage coming because of the hail dropping and hitting things, but you've also got damage coming because there's a lot of wind going on.
Yeah.
You've got damage because it's raining,
Yeah.
a lot of rain, and I think many of those big loss events, so this
Has a significant flooding component and things.
Flooding.
Yeah, that's right. Yeah. Yeah.
So it's a very complicated set of calculations, and again, you touched across several of these. We've got a pretty good building code, so we don't anticipate these extremes, but we anticipate these kinds of things.
Yeah.
So again, how would the damage differ for a commercial structure
Yeah, sure.
compared to a home?
Sure. Okay, so
Take Calgary. Just tell me.
for Calgary, sure.
All that damage.
Okay, so one, let me be clear. The losses I showed here, only from the hail component. Hail component and wind-blown hail, not wind damage, wind-blown hail and the hail. Nothing, no flooding, no precipitation. This is just the hail component. So I just want to make sure that that's clear. Now, in terms of the way that the damage is happening, so for hail, anytime you have glass, that's where you see a really high amount of vulnerability. So one, auto, right? Auto just sitting out. Auto dealerships are particularly vulnerable when they have open air inventory. There's no way for them to actually move that inventory anywhere. That's one of the things. For commercial structures, just now, I will admit I've never been to downtown Calgary, but I would bet that there are glass skyscrapers in downtown Calgary. That glass is obviously rated for some level of impact resistance. They're not going to just put some thin pane glass up there. But we have seen, more so in tornado events where we have wind-blown debris, but also in hail events, that we can see significant damage to the facade of that building. So now, you're not going to collapse a building with hail, right? You're not going to see a skyscraper fall because 4-inch hail hit it, but what you are going to see is a significant increase in damage due to the fact that you have to replace all of the window panes for the entire city, basically. So there's a lot of loss from a commercial side of things due to those type of glass facades. There's also things that are on top of the buildings, maybe roof-attached structures that are very vulnerable to hail because they're out in the open. So we get a lot of those that get hit. And then the other component is that if you get big enough hail where you're starting to puncture the envelope of the building, you're going to get water leakage into the commercial structure. So think of all of the networking, all the equipment that is in the ceiling of this room here, all that once the water starts getting in there, it's basically all shot. And so there's also a significant component of content damage. That's only when you start to get sort of this water infiltration here and you start to get actual punctures in the facade and in the roof of the building itself. So for commercial structures, I think that's sort of where it's really coming from. Glass facades, content damage due to water infiltration, and then any of these particular industries that are really vulnerable, that have a lot of open air inventory that they're not going to be able to get out of the way. Residential structures, obviously, when you have wind-blown hail, there's a lot of damage to the siding and the cladding of the building itself. I think actually when you have events, typically most of the loss of residential structures is actually from the roof. It's about 30% of the TIV. You basically have all this hail, it destroys the entire roof and they get it replaced. When you start seeing wind, you tend to see a 50-50 split between the roof damage and actually the siding damage as well. So for residential structures, it sort of depends a little bit on how much of that horizontal component. Same thing with the commercial structures. You need to have hail basically being blown horizontally into those glass panes to start seeing some sort of damage to them. So that's sort of how I envision an event going down, not knowing too well the exact makeup of the structures there.
So it really helps me a lot. So in part, in terms of the insurance claims, you're saying it's going to be worse because you've just got the hail part, and we know there'll be some wind. There'll be some
That's right. Yeah.
But it's not yet in these large numbers.
Right.
Can I push same thing, but take you to Halifax for a moment? It's my sense with the category 1 and 2 hurricanes that we see more often, metaphor, that our mix of the damage that comes because wind does cause trouble, but compared to Florida and the Gulf and whatever, we don't have the same kind of wind.
Yeah, right.
Not with the frequency or whatever. And so by the time it gets to Canada, it's really raining. We're getting flooding things. Just as in the U.S., there's a mix of flooding and wind, but I think our combination has more on the flood side as of just how far it gets here.
Sure, yeah.
When you've got a scenario here where it's a Category 4, so we got a real lot of wind coming this way,
Yeah.
but it's probably also raining.
Yeah, that's true.
So the rain's not part of your story except if the wind creates a hole and the water gets in, but...
That's right. So water infiltration is included, and some flooding, if it's implicit, like sometimes it's difficult to get that out of the claims data because it sort of leaks in. I think they call it claims leakage. There's some percentage of claims leakage involved in the calibration of the model, but there is no explicit hurricane or tropical cyclone-induced flooding yet.
And storm surge?
So storm surge is typically so it depends on where you are in the country. We're in the middle of developing brand new storm surge models sort of across the globe. We just put out the US one recently. I don't know, Kunal, did you have the details on Canada from storm surge perspective?
Maybe during the next update.
I believe it's, I should check to see how much of that is included in the current. Because I know in the US, at least before we had an explicit model, there was some accounting for it. In the losses, but I'd have to double check for sure for the Canadian ones. I don't want to tell you something.
At the moment, it's largely not covered.
Yeah, right. Yeah.
So there's the economic loss.
Yeah.
Insured loss.
Well, it's not officially covered, but then you always get to the insurance company won't pay my claim. It's the political claims. Hold on one second. Yes.
When you run your models, the vulnerability of the structures is important, I'm guessing. And well, right now in Canada, we're building a lot of wind farms.
Mm-hmm.
And I've been involved in the last several weeks with that. How do you model wind farms in your catastrophe?
Now, I'll have to go back and check exactly how they're handled in Canada. I know in the U.S. There's an explicit treatment of them separately, but I'll have to see if that is being included in the Canadian damage fund. Normally, if it's in the U.S., it tends to be in Canada, but not always. But it depends on how much data we have on the Canadian structures, how much they differ from the U.S. structures in terms of the vulnerability and mechanistically, but I'll have to look and let you know for sure. But it's definitely something that's on the radar, and depending on the market demand for it, we tend to start developing explicit damage functions for them when there's really a demand for them. So something that we look at all the time. I just can't tell you for sure about the Canadian ones. Sorry about that.
One of the things I think that might be interesting, especially when you're doing damage assessments, is how to deal with IT now. Because you take some of these previous damages, you may not have looked explicitly at IT, and a lot of the things now, especially how now everyone's so heavily dependent upon it, and it's getting more dependent, cutting off, say, a data center or something could really, really cause a lot of issues.
Yeah.
And I do know that a lot of IT firms just don't do a lot of natural hazard modeling.
Yeah.
You could talk, for example, about a T4 data center, and that's the best sort of data center around, dual power feeds, dual feeds for data. You could theoretically be on either side of a slip fault on the side of a volcano. It would still be a Tier 4 data center.
Right. Yeah.
So something like this, if your data centers are positioned too closely and so on, you could really, and you're dealing with a financial organization, you really could jump your losses very, very heavily, very quickly.
Yeah. Well, I think so we don't explicitly treat something like that in the model right now, I'll say first, but I think what's even more interesting is what if your IT is located off-site?
Yeah.
And your insurance policy, so the event's actually not occurring anywhere near your actual structure, but it is interrupting your business because it's hit your IT center. That's actually sort of an interesting thought that I don't think too many people have really considered too much yet, actually. Yeah. That's a good point.
Interesting, because I teach IT risk assessment at George Brown, and one of the things I've been trying to do is take the IT people out of their data center and actually do some geographic assessment just by Google Earth, just qualitative work to see where are you and what can affect you.
Where's the closest floodplain? Where's
And you'll find a lot of data centers literally are sitting on either side of the in California.
Yeah. Yes.
Same areas I was asking before, but it moves to the Toronto event. So again, we had the large storm in '98, and then we've had some that we consider really big, but it's a couple $100 million of insurance claims.
Yeah.
So you're jumping big time here in terms of what is possible if you just take that Montreal event and move it to Toronto.
Yep.
Can you help us understand, so what actually is the insurance coverage for?
Yeah.
damage to buildings, or is it just the interruption because the
Yeah.
power's out?
So it typically comes in two, well, I mean, there are three main forms. So you can have damage to buildings, right? You can have the ice accumulate on eaves and troughs and start splitting sort of the corners, and then you get water in there. So, you know, that typical type of, that's almost like a ice damming type of damage that you're used to. The two other types that really come into play for ice storms, particularly ice storms like this, that are going to be so extreme, they're going to be business interruption and content damage. And let me talk a little bit about, so business interruption may be kind of obvious. The power's down, you can't do your business, and so depending on how long it takes them to get the power back up, you know, your losses are going to accumulate throughout. 98, some places it was a month. Thankfully, most places it was not a month, but there is significant business interruption losses from that. Relocating people that now don't have heat in their houses, you know, there's a lot of loss associated with that. To the point of content and not having heat in your house, actually, interestingly enough, one of these brochures I picked up from you guys mentions one of the main drivers, and that is once you lose the heat, you basically lose what's protecting your pipes, right? And so with prolonged electricity outages, those pipes are no longer being heated internally, and you're going to start to see those pipes start to burst. Even if you rely on natural gas for heat instead of electricity, you still have fans and blowers in your system that are running on electricity. So the system itself still can't necessarily operate the way it should. And so you're not going to see that type of protection due to the heating of the house. So I think by and large, it's going to be losses from those types of things. So then you start to get also physical damage from the water inside the house and the pipes burst and things like that.
Again, I can suggest, but I'm looking for your advice here. If you look across the history of the 10 larger Canadian events, most of them have had a predominance of residential claims. And the one that stands out that was a bigger commercial hit was the flooding in Calgary. The water got into the downtown, and the numbers on the commercial side just stood out. They were just quite a bit bigger for the Calgary event. And we're not we're not sure yet about the wildfire in Fort McMurray. If you look at damage to structures, there's going to be a commercial component because it's a big event, but it's mainly the residents that burn to the ground, and it's unclear whether there's business interruption or some other commercial claims that are going to show up in Fort McMurray. So that one we're watching on. But most of these have been residential. So of the three big scenarios done here, I think the ice storm is one where you were telling about some of the things that could be residential, but I think it's got a heavier commercial component here.
I'd have to, I think when I looked at the loss, at least that's coming out of the model, it's also, you have to be careful because it scales with exposure value too if you're looking just at percentages. It was, I think, actually a little bit more in favor of residential in the model, but not, it's not like 80-20, it was something like 60-40 for the most part. I'd have to look to get those numbers exact, but you know, they're comparable, but maybe not equal. And I remember it being more on the residential side. But yes,
when you're developing your model now going forward, are you spending a little more energy now to take into account